Hello there, welcome back. We're starting our next video in the fluids unit, and today we are talking about buoyancy force. So buoyancy force, you probably already have a little bit of experience with this. If you've ever taken something and thrown it in water, you might notice that some things tend to float and other things tend to sink. And so this, of course, is all explained by this idea of buoyancy. If something is buoyant, then it floats. And you probably already have the idea that it's going to depend not just on the material itself, but on the fluid that you're trying to float in. You might realize that this block B here, this yellow block, is floating because it's less dense than the water it's in, whereas block C sinks because it's more dense. And you can see that even though they have the same mass, they have different volumes. And so the more dense you are, the more likely you are to sink. But just recognize also that there's a buoyancy force acting on both of these things. And so, for example, if I take block B and I drag it and force it to submerge under the surface, there's a force upwards that is pushing up on it all the time. And it's going to try and restore it back to that surface. The same thing's happening with C. You can't see it because C definitely sinks, but you might have had the experience of trying to pick up something underwater. Like imagine a really heavy rock and you pick it up underwater and it doesn't feel all that heavy until you get it to the surface. And all of a sudden, when you try and lift it above the surface of the water, it becomes much more heavy. So this is all explained by the idea of buoyancy force, which is whenever you have an object that's submerged or partially submerged in a fluid, there's going to be some sort of force upwards that's trying to bring it back towards the surface. So we see that submerged objects have a buoyancy force, and this can be thought of in a couple of different ways. So we're going to try explaining it two different ways. The first way is to recognize that if you have an object that's underwater, as you increase with depth, we saw that pressure increases with depth. So by that I mean the pressure on the object caused by the fluid that it's in is getting greater the deeper down you go. So what that means then is if you have an object, like take this little rectangular prism sitting in water, the further down you go, the greater the pressure is, which means the top of the object is going to experience a different pressure than the bottom. So there's a pressure force here on both the top and the bottom. There's a pressure force that pushes down here. I'll call this P top. And there's a pressure force that pushes on the bottom of it. And so the pressure on the bottom is going to be greater than the pressure on the top. And so this creates there's a difference there, right? And this results in an overall upwards force, an upwards buoyancy force on the object. So we can actually kind of derive from this idea an equation for the buoyancy force. And so I just want to point out before we get into that, just recognize that there would be pressure on all the sides of this as well. There'd be like a pressure here pushing it on this side, call it P side, and there'd be a pressure on this side here, also P side. Just recognize that those two pressures would be equal. And so even as you go down the object, the pressure on the lower part would be pushing in, but it would be equal on all the sides. And so the only real differential is between the top and the bottom. So if I wanted to calculate, for example, the pressure on the top here, I could find that P top is equal to rho GH. And maybe I'll call this H1, where H1 is how far below the surface you are. And we learned that formula last day. So similarly, then the pressure, at the bottom, P bottom, would equal rho GH2, where maybe H2 is the height below the surface to the bottom of the object. We'll recognize now what we've created here is that there's a difference between these two. And I might call this distance from here to there, I might just call that delta H, which is the difference between the top and the bottom surface, which really is just the height of the object itself that's sitting in the water. Okay, and so what we recognize is the pressure on pushing up on the bottom of the object is definitely going to be greater than the pressure on the top. And you might think about the difference in the pressure just being the difference between the bottom minus the pressure on the top. And that overall pressure is going to be pushing in the upwards direction. So we can relate this to forces because we know that pressure is equal to force divided by area, which means that force is going to be pressure times area. And so the overall upwards force is going to be that pressure differential, that delta P, times the area. So we know that pressure differential is going to be rho G delta H, and that whole thing is multiplied by area. But recognize that delta H is the height of the object, and area is the surface area of the top and bottom of the object. And so this whole thing right here, you might remember, is really just volume. volume is just area times height. So this whole thing simplifies down to say that force is rho times V times G. So this is one way to think about how buoyancy force works, that there's a differential in the pressure on the top and the bottom of the object. And recognize that I used a really simple object here, like a square or a rectangular prism. It doesn't matter the actual shape. The derivation would work out to give us the same result, regardless of what it is. This one just made it easy on me. So the other way to think about this is to jump back to this little simulation here and look at what's happening when we displace water. So if I take block B, for example, you'll notice that if I pull it out of water so it's not displacing quite as much, then it wants to sink back in. And if I force it to submerge, it's going to displace more water, but when I let it go, it's going to bounce back to the equilibrium point. This is the point where the buoyancy force that's pushing up on the block must be equal to the weight pulling down on the block. And what you've noticed is it's going to displace a certain amount of the liquid. And this is something that Archimedes noticed a long, long time ago, which is the block is just going to displace as much liquid as it needs to in order to counteract its own weight. So this follows something called the Archimedes Principle that says a submerged object will experience a buoyancy force equal to the weight of displaced fluid. Now, notice that this accounts for a situation where we float and one where we sink. So in this case, my block is floating, and it's just going to displace as much water as it needs to in order to equal its own weight. If I take a more dense block and drop it in there, this will still experience a buoyancy force. It's just that it can't displace enough water to account for its entire weight because it's more dense than the water or the fluid that it's in. So, using this idea of the Archimedes principle, the buoyancy force is just equal to the weight of displaced fluid. So again, two ways we can think about this. We can think about the buoyancy force as being, the buoyancy force is just equal to the displaced weight, so the Fg of the fluid, and so that would just equal mg. It's really important to recognize here that in this case, what we're talking about is of the fluid itself, not of the object. So these are both of the fluid. And then the other way that we could calculate buoyancy force would be to use this other formula that we derived over here, which is to say that Fb is equal to rho Vg. And again, we just need to recognize that in this case, what we're talking about is the density and the volume of the fluid. Now, you'll see in some cases we can use the density and the volume of the object, but only if the object is completely submerged. So it's safer to just use the fluid. Okay, so we're gonna do some calculations here and see if we can use our fancy new formulas. So crown weighing 8.3 newtons is suspended underwater from a string. The tension in the string is measured to be 7.81 newtons. Is the crown pure gold or not? We've got the density given right there. And this, of course, goes back to the famous story of Archimedes, who apparently was able to determine whether or not a king's new crown was made of pure gold just by testing for the density, by submerging it in water and then analyzing it. Now, hopefully the king's crown looks nicer than mine, but that's all we need to do. So we've got it submerged in water, and there's a tension force pulling up here on the crown. So there's a tension force, and then there's a buoyancy force that's also supporting the crown, Fb. And then of course there's a weight pulling down. So this is a good example where this object would sink, but because we're supporting it with an additional tension force, then it floats. So the first thing to recognize is we can find the buoyancy force, because we know that, for example, Fg would just equal Ft plus Fb. So those two up forces are the same as that one down force, which means the buoyancy force is just the difference between the weight and the tension. Okay, so I've got 8.30 minus 7.81. So my buoyancy force is 0.49 newtons. Okay, so that's my buoyancy force. And now what I can say is, okay, so the buoyancy force we know is equal to rho Vg. So we could calculate the volume of the crown. So V is going to equal Fb over rho g, which is 0.49 newtons divided by the density of the fluid, which is 1,000, because it's in water, and g, 9.8. And so we end up with a volume. It's quite small. It's somewhere around 4.8 times 10 to the negative 3 cubic meters, which again makes sense because it's just a crown. So last but not least, we can find the mass of the crown. All right, so we know the weight of the crown, Fg equals mg. So that means we can find the mass of the crown is Fg over g, which is 8.30 over 9.8. So the mass of the crown is 0.8469 kilograms. And then last but not least, we can find the density by dividing these two. So the density is going to equal mass divided by volume, which is 0.8469 divided by 4.8 times 10 to the negative 3. And after all that work, we end up with a density of right around 17,000 kilograms per cubic meter. So the question is the crown pure gold? And that's a big no, because the density of whatever metal it's made of is not that of pure gold. Okay, so next question. We've got iceberg floating in seawater, which is extremely dangerous because and you might know this, that most of what you see of the iceberg is actually not most of the iceberg. Most of the iceberg is submerged underwater, and that's because the density of the ice is just slightly less than the density of the seawater. So it's going to float, but most of it is going to be submerged. It's floating in seawater, and so one thing we should recognize here, the density of seawater in this case is going to be 1,030 kilograms per cubic meter. If you were finding, like, say it was like pure water, maybe ice floating in a glass, it'd be slightly different. So the hidden ice can damage the ship, and that's because only a fraction of it's visible from the surface. So what fraction of the iceberg lies below the water level, and the density of the ice is 917 kilograms per cubic meter. So let's just draw a little picture here because pictures help. So we've got an iceberg, a little bit sticks out of the water there, and then we've got our water level. Okay, so recognize that in this case, I've got a situation where the weight of the iceberg pulling down is going to equal the buoyancy force pushing up, right? Because it's just floating static in the water, and so those two forces must equal each other. So I might start off actually with something like that the buoyancy force is just equal to the force of gravity, the weight of the iceberg. So the buoyancy force of the iceberg is going to equal rho times V times G. Now just recognize that that is the density and the volume of the displaced water. So I might just put a little W beside those, the density of water and the volume of the water displaced, just to kind of keep that in my mind. And that is going to equal the mass of the iceberg, maybe we'll call it MI, times G. Well, we know that mass, since density is just equal to mass divided by volume, we know that mass is going to be density times volume. So I could bring this along here and sub it in there for my mass, and I end up with an expression that looks like this. I've got the density of the water times the volume of the water times G is going to equal the density of the ice times the volume of the ice times G. And two fun things happen here. One, G cancels out, which is nice. But this leads me actually to what I'm looking for. I didn't actually really stop and think about this too much, but the question is asking what fraction of the iceberg lies below water level. So I could rearrange this equation here to say that the volume of water divided by the volume of ice is going to equal the density of the ice divided by the density of the water. And this is actually the answer I'm looking for, because this is the ratio of submerged ice to total ice. So this is going to equal the density of the ice we know is 917, and the density of the water is 1030. So this gives me a value of right around 0.89, or about 89%. Okay, and so that's going to tell me that of the total amount of ice, 89% of it is actually submerged in water, so that it provides enough buoyancy force for it to float. Okay, we got one more question, and this one is a doozy, a bit of bit of a classic AP problem. So we've got a large raft floating in the water, and it's sitting on a lake, and the surface area of the top of it is 8.2 square meters. The volume of the whole thing is 1.8 cubic meters. The density of the lake water is 1,000 kilograms per meter cubed. So first thing to notice is that the raft sits submerged, but not entirely submerged in the water, and that's because it's less dense than water, 650 versus 1,000. The first thing it wants to find is calculate the height of the portion of the raft that is above the surrounding water. So how much of the raft is left over? And just before I do that, I might just define a couple other variables here, just so I've got them clear. So I'm going to call this height right here, I'm going to call this height HR for the height, like the total height of the raft. And then maybe this H right here, I'm going to call this HW for the height of the raft that is submerged in water. And then of course you can see here that HR is really just HW plus H, which is the amount we're trying to find. Now, you can actually solve this using the same idea we did in the last question by finding the proportion of submerged raft and then kind of using a ratio. And you could go ahead and do that this time too. I'm going to solve it a slightly different way just to show that there's more than one way to kind of attack these problems. So, okay, so calculating the height of the portion of the raft that is above the surrounding water. All right, the first thing to recognize is that this raft is floating, and since it's floating, isn't that nice of it? Then we know that the buoyancy force is equal to the force of gravity, the weight of the raft. So I could say rho Vg, and this is rho of the water times the volume of the water times g, is going to equal rho raft times v raft times g. And that's just because the weight of the raft must be equal to the amount of displaced fluid. And so again, I get a situation here where G is going to cancel out. And so I could find the volume of water displaced by just solving this equation here. I've got V water is equal to the density of the raft times the volume of the raft divided by the density of the water. And so the density of the raft is 650. The total volume of the raft is 1.8, and then the density of the water is 1,000. So that ends up being right around 1.17 cubic meters. Now it's important to just kind of keep in mind what the heck we just found. We found that this raft has to displace 1.17 cubic meters of water in order for it to float. So that's the displaced volume of water. So if I know the displaced volume of water, then I could figure out the height, because I know that volume equals area times height, and so the height is just going to equal the volume divided by the area. And so this is the height here, again, the height of the water. So the volume of water displaced is equal to the area of the raft times the height of water. And so that is going to equal 1.17 divided by the area, which is just the area of the total raft, which is 8.2. And this gives me 0.143 meters. So this is telling me the height of the water. That's telling me this number right here that I found. And so the only thing I need to do at the end is to say, okay, well then the difference between those two, so the height is really just going to be the height of the raft minus the height of the water. Now I haven't found the height of the raft yet, so if I go back up here, I could do that and say, okay, the height of the raft is dependent on the volume. So volume is going to equal area times height, volume of the raft, and so I could solve for the height of the raft. Height of the raft is going to equal the volume of the raft divided by the area. So that's 1.80 divided by the area 8.2, and this ends up being 0.220 meters. And so bringing that all together here, I could find the height that's above the water, and that's just going to be the difference between the height of the water and the height of the raft. I'm saying the word height an awful lot. So 0.220 minus 0.143, and so the overall height here that's above the water is 0.077 meters, and that is the answer to the first one. So all that work was actually just all for part A. All right, so that was good on us. The next question says, okay, so what is the magnitude of the buoyant force on the raft, and state its direction? Well, the direction is pretty obvious. The buoyant force has to be upwards, but let's see if we can find out how much it is. We'll do that over here. So the buoyancy force on the raft is just going to equal the density of the water times the volume of water displaced times G. And I know all those things. So I've got 1,000 for my density. And the volume of water displaced I found earlier in that first part. So 0.143. And I multiply that by G. And I end up with quite a bit of buoyancy force. We end up with 11,500 newtons is my buoyancy force. And then the last question is saying, okay, so if the average mass of a person is 75 kilograms, how many more people can we put on this raft without the top of the raft sinking below the surface of the water? And we'll assume the people are spread out evenly and the whole thing doesn't tip over in the process. So in order to figure this out, what I need to think about is, okay, I've got a certain amount of height left over. Like there's a certain amount of extra buoyancy force that I can possibly access before that sinks under the water and then the whole thing starts to sink. So the additional, this is just the additional buoyancy force is really just going to be related to how much height is above the water. So that's going to equal rho vg, but in this case it's going to equal rho times the area times h. And h, remember, is this little, it's this height right here. It's how much height I've still got left over. So that's my additional possible buoyancy force. And I can calculate that, and that's going to equal, so 1,000 times 8.2 times 0.077 times 9.8 for G, and this is about 6,188 newtons. Now, the clever amongst you might have realized that we could have actually just figured that out as a proportion using the previous amount of buoyancy force, but whatever, we're here now. So I know how much extra buoyancy force I've got. So I could say, okay, fine, so how much mass will that be? So I know my buoyancy force is going to equal the weight that I've got available, which equals mg. So the additional mass that I can carry is just going to be the buoyancy force divided by g. So 6188 divided by 9.8 means I can carry about 631.4 kilograms. And then so last but not least, how many people is that? Well, the number of people is just going to be that total number of mass, 631.4 kilograms divided by 75 kilograms per person. So that gives me 8.42 people, which typically that's not going to work. And so let's just round that off and say it's going to be about 8 additional people that we can carry on the raft. Okay, that is it for buoyancy force.